Real numbers are essentially any number we can place on a number line. These include 0, 1/2, 1, pi, 1000, minus pi, minus 1, minus square root of 3, and onward for the negatives. What are exceptions to real numbers? What would not qualify as something we could put on the number line? Well, one example would be infinity. Infinity is at the end, always beyond the extension of the number line. It can never be placed exactly on the number line. Another example is imaginary numbers. And as the name suggests, they are not real. And these are denoted by the letter I, and it's defined as the square root of -1. How could and where would we put the square root of a negative number on the number line? Would it be positive? Would it be negative? If I took -1 and squared it, well, that would be a positive result. And of course, +1 squared would also be a positive result. So how is it possible that the square of an imaginary number in this case could have a negative result? It's not something we could therefore place on the number line. However, we do know that I squared is -1. The square root of -1 squared will just be the result in the radical, which is -1 in this case. And that actually is a real number. -1, or I squared, we can put on the number line. In fact, any even exponent of I we can place on the number line. Any odd exponent of I cannot be placed on the number line, as it will be an imaginary number. Even I cubed will essentially be I squared times I, or -1 times the square root of -1. In either case, real numbers are not to be confused with rational numbers. Rational and irrational numbers both are subsets of real numbers. But the definition is very different. Whereas real numbers are anything you can put on a number line, a rational number is any real number that can be expressed as a fraction of integer values, which I'll denote by p divided by q, where p and q are themselves integers. What are some examples of rational numbers? Well, 1/2 is two integers expressed as a fraction. 1/4, 3/8, all rational numbers. Even 1/3. But wait a second, 1/3 is actually 0.33 continuing infinite decimal, unlike 1/2, 1/4, or 3/8. Is that too rational? Well, yes, of course. It's not the infinite decimal part that matters. It's whether the number can be expressed as a fraction of integer values. And in this case, any repeating infinite decimal will be a rational number. Irrational numbers, however, are not crazy. They're just numbers that cannot be expressed in the simple fraction format, p over q. Some examples of irrational numbers include pi, phi, the golden ratio, square root of 3, square root of 2, e, the natural log, one you won't be required to know for this course. And you might notice that each of these is an infinite decimal. The difference between that and the rational infinite decimals is these are not repeating. So a non-repeating infinite decimal will ultimately not be able to be expressed as a fraction, and that is the real definition. The irrational numbers, if written as fractions, would be continuing fractions. So for example, phi, or the golden ratio, which we'll see later as we cover Fibonacci sequences in another lesson, is a simple continuing fraction. It's 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over, and so on. I could keep going infinitely. It cannot be expressed as a simple fraction of p over q. We can, however, make estimates as we iterate the fraction over and over. So for example, the first iteration is 1 plus 1, or 2, as an estimate for the 1.618, etc., continuing decimal. Or I could go a level further for the next fraction, and that's 1 plus 1 over 1 plus 1, or 1 1/2. So we're again closing in on 1.618. And then if I went down and incorporated the next level of fractions, it would be 1 plus 1 over 1 plus 1. So 1 plus 1 over 1 plus 1/2, or 1 2/3. And you can see we're bouncing around the value of the golden ratio and eventually zeroing in on our 1.618 continuing decimal, all from a continuing fraction. And the same can be said for pi, for example. Pi expressed as a continuing fraction will be 3 plus the reciprocal of the 0.14159, etc., would roughly be something like 7.0625. So expressed as a fraction, 1 over an integer, the nearest denominator would be 7. That's not greater than the number. So that would be our second level of our continuing fraction. And by the way, not surprisingly, when we look at an estimate of pi for the exam, you're often taught to use 22/7, which didn't come out of thin air. It is the second level of the continuing fraction that expresses pi, not a simple fraction of the form p over q. But that is a fairly accurate estimate. With just one level in, your result is going to be 3.14 something something something. Not exactly pi, but very close very quickly. And if we continued that exercise, we would eventually get 1 over 15 plus 1 over, and we would continue onward with a never-ending continuing fraction. Likewise, if we look at, say, the square root of 3 or square root of 2, we could also note that the square root of any integer that's not itself a perfect square will be an irrational number. 3 is not a perfect square, 2 is not a perfect square, so the square root of those numbers will be irrational. Likewise, the square root of 5, 7, any prime or any integer that's not a perfect square will be irrational. It should also be noted that any multiple of an irrational number, say 3 times the square root of 3, will also be irrational. In fact, more generally, that's just a combination of a rational number and an irrational number. And any combination of rational and irrational, whether the operation is addition, subtraction, multiplication, or division, must be irrational. Now, of course, combinations of rational numbers will be rational. However, combinations of irrational numbers and irrational numbers will often produce irrational numbers, but not necessarily. One simple example might be square root of 2 times the square root of 2 will result in 2, which is a rational number and is expressed as a fraction. Integers can always be expressed in the form the integer over 1 as a fraction. So hopefully this will help you identify rational, irrational, and real numbers. And that will be important on the exam because often cases the sets of numbers you're required to manipulate are defined by these terms, real and rational numbers. And without understanding and identifying them accurately, there's no way to get the rest of the problem correct.